that Barry just mentioned. And I'm going to be talking a bit about work that we've been doing in identifying cold streams in TNG-50 and looking at their properties. First, to motivate why we're doing this a bit, just looking at the cosmic star formation history as a function of time in this classic Maddow and Dickinson plot, we see that there's this clear peak at around cosmic noon or redshift 2. And at cosmic noon, we have these large star-forming galaxies that have star formation rates on the order of 100 to 200 solar masses per year. When you compare that to the present-day Milky Way star formation rate of 4, that's obviously a huge discrepancy. So a big question is, how are these galaxies able to sustain such high star formation rates? And if we look at the picture of how halos accrete mass, in the classical picture, there are two main modes of gas accretion. A hot mode accretion, where hot halos shock heat inflowing gas, and this is especially dominant in massive halos at low redshift. A cold mode gas accretion, in which gas falls into halos as cold filaments and is not shock heated, and this is especially dominant at low mass halos. But there's a third regime at high masses where there is a hot halo, a hot CGM, but gas is able to fall in cold filamentary structures without being shock heated. And this is thought to be how these galaxies are able to be provided with enough gas to maintain such high star formation rates. And this has been looked at in detail over the past 20 plus years in simulations, both on the cosmological side and the idealized simulation side. So I have a few examples of some papers where they've looked at this in cosmology, and they've looked at the presence and confirmed the presence of these cold streams. They're ubiquitous across different simulations. But as Barry mentioned, one key problem is that these simulations lack the resolution in the CGM to properly resolve the interaction with the stream, and the prediction of how far these streams are able to penetrate into the halo and thus provide galaxies with gas is vastly different depending on what simulation you're looking at. And on the other hand, there's a paper series led by Nirmal Delkar, for example, where we look at idealized simulations, and there we can resolve the instabilities that are affecting this penetration better, but this again is idealized, so we're missing the cosmological context. So what we really need is something that combines both of these, where we have high resolution in the CGM and a cosmological box and cosmological context. So we're working on approaching this in two phases. So the first is to look at existing cold streams and some of the higher resolution cosmological simulations that exist now, and identifying how prevalent they are, bracketing around cosmic noon, and then from these simulations we're extracting initial conditions to run our own high-resolution zoom-in simulations with the goal of 50 parsec spatial resolution throughout the entire volume of the CGM based on the spatial refinement technique presented in Van de Voort 2019. So I'm going to talk a bit about the results we've gotten from looking at TNG-50 so far. And the reason we chose TNG-50 is because it has fairly good resolution for a cosmological large box, and it's large enough that we have a statistical sample of these massive halos above 10 to the 12. As Barry mentioned, the spatial resolution in the outer CGM is in general around a kiloparsec or more on average, but around 200 to 300 parsecs in the dense regions. And the mass resolution for baryons is also listed here, around 5 times 10 to the 4 solar masses. So we look at Illustris TNG-50 snapshots from redshift 4 to 0, and we select halos with virial mass, or M200C, of above roughly 10 to the 12 with a little bit of wiggle room. And we've developed novel algorithms to firstly automatically detect streams in the halos and then extract stream physical and geometric properties. I'm going to walk you through a bit how we detect the streams. So first, we take a halo and select all gas between 0.15 R200 to remove the ISM contribution out to 3 times R200 to include the further out lengths of the flows. And then we remove subhalo particles to avoid contamination, and we filter to only look at cold stream-like gas, which we define to be gas that is colder than 2.5 times 10 to the 5 Kelvin, relatively dense, 3.5 over centimeter cubed, and inflowing with a magnitude of inflow about a quarter of the virial velocity, and also with most of the velocity being radial compared to the total velocity. And we're left with something like this. And then we use the density clustering algorithm HDB scan to identify substructure within these gas particles, and we merge, because sometimes these are a bit fragmented, so we have a way to merge what should be one stream together. And then finally, we look at the resulting clumps or streams, and we filter by the properties and identify stream-like substructures, like this example where we have 3 stream-like structures. So we run this on Illustris TNG 4 through 0 redshift snapshots, and we find that streams are prevalent at high redshifts out to about redshift 0.5, where it starts to decline significantly. At redshift 2 and 1, we really see a peak in the standard picture of 3 cold streams configuration. But when looking at both how prominent they are and how much mass flux they're actually providing, we estimate that around redshift 2, we're seeing the most strength in mass flux. And here I'm showing a couple examples of the halos that we're looking at redshift 2. This first one is a halo at mass 10 to the 12.81, and I'm showing the density map projection, mass flux projection, and temperature projection. And here we can clearly see the dense structures, the inflowing stream structures. And here at the bottom, there's an example of a 3-stream configuration. Taking those maps and taking our stream-like gas, we can measure the typical properties, physical properties of the streams. So here, for example, on the left, I'm showing the typical temperature of the streams as a function of redshift. And we find that around redshift 4, it's around 10 to the 4.2, and it increases slightly as we get to lower redshift, whereas the density remains about constant, but then decreases a bit towards the low end, or the lower redshift end. We've also looked at the degree of coplanarity between the streams in halos that have 3 or more streams, where a coplanarity angle of closer to 0 indicates that these are more coplanar, or in one plane roughly, which is what we would expect in the classical picture, where a higher angle would be closer to an isotropic configuration, which is not really what we would expect in this classical picture. And we find that at redshift 2, we do have the lowest peak in coplanarity angle. Redshift 1 is going towards the end where it's more isotropic. We don't look at the lower redshifts snapshots because we have negligible number of streams, so we don't include that. And the next step, we develop an algorithm to detect the max penetration depth of the streams. And this is based on hammer plots of mass flow. So we make mass flow hammer plots at various radial shells going inwards. And then at each step, we identify regions of strong inflow, and matching between hammer plots or consecutive radial shells, we see where they maintain the same location or the same structure. And then we define the max penetration depth as the last radial, most innermost shell, where we find the same kind of inflow. These are the results of the mean stream penetration as a function of redshift here on the left, where we see that the mean penetration decreases or increases, it goes deeper into the halo as a function of redshift, down to redshift 0.5, where then it increases again. And in general, the deepest that we go is about 2/3 of the virial radius. But I guess a point Barry really brought up is, can we actually trust these numbers? No, because TNG-50 doesn't have the resolution to resolve the physics of this stream CGM interaction that's really going to govern whether these streams survive. And that's why, as Barry already mentioned, we are working on a suite of zoom-in simulations where our goal is to run approximately 20 cosmological zoom-in simulations with a repo in TNG physics, mostly focusing on the evolution from redshift 3 to 2, with initial conditions extracted from the halos we've looked at in TNG-50. As a base, we're increasing the mass resolution in general by a factor of 8, which will be about the same as the highest IPM simulation that's been run. And then in addition to that, we will impose a spatial refinement criteria within the volume of the CGM and the surrounding area with a goal of 50 parsecs, but really to see how far we can push that to hopefully resolve some of these interactions. I think that's it, so I'll just leave my summary up, but I welcome any comments or questions or feedback. Thank you.
Okay, we have time for a few questions. I think I see Haley.
Hi, so this is really neat. I was wondering, you talked about the alignment of the streams themselves. Did the streams tend to be aligned with the galaxy as well, or?
We haven't actually explicitly checked that, but that's a good point. That's something we should add to that talk. Thank you for the suggestion. Mm-hmm.
Physical cooling arguments?
Yes, so we chose 2.5 times 10 to the 5 because that's what's classically been used to distinguish the cold and hot mode accretion in literature, for example, in the Keras et al. 2005 paper. And others have tested this criterion by looking, for example, as a fraction of virial temperature, and they find that that's not the standard cutoff works better, or an entropy-based cutoff actually works about equivalently to this 2.5 times 10 to the 5, and that is based on the cooling function.
Okay, any final questions for Isa? If not, let's thank Isa again.